Now if we look at the same 5 microcoulomb charge at the origin, remember our point 0.3 meters, negative 0.4 meters, was at a distance of 0.5 meters from the origin. If we draw a circle representing the sphere actually that surrounds this point with radius 0.5 meters, we see that the magnitude of the electric field has to be the same everywhere on this sphere because every point is at the same distance from the 5 microcoulomb charge. We see also that the electric field has to be directed outward, radially outward from this point at every one of these points. Okay, so at every point on this sphere we have a radially directed electric field directed straight away from the origin, which is where the charge is, of the same magnitude over this entire 0.5 meter radius sphere. If we come out to a radius of 0.81 meters, and remember that the second charge was at approximately 0.81 meters, we see that the electric field has strength 68 kilonewtons, as opposed to the 180 kilonewtons that we had on the 0.5 meter sphere. Okay, so all these vectors here are 180 kilonewtons. All the vectors on this sphere are 68 kilonewtons, just a little more than a third of this. Remember that the electric field falls off inversely as the square of the distance. It essentially falls off as the area of this sphere, in fact. Okay, and that's, of course, the flux picture that we'll talk about in a minute. So that we can draw these vectors, in any case, all the way around this sphere. And each vector represents the 68 kilonewtons. And we notice that these vectors are about a third as long as these, indicating the relative strength of the field. Now we can draw what we call field lines. The field lines have the direction of the electric field at every point. So we have field lines coming out, of course, always in the radial direction, because from a point charge, that is the direction of the electric field at any point. Reason being, of course, because that's the direction of the electric force experienced by a test charge at any point, straight away from the charge that's creating the field. And again, this is just the field of a single charge, the field of a 5 microcoulomb charge, nothing else. On each of these spheres, there's an electrostatic flux. Okay, we can represent one of the spheres maybe by this concrete ball. Imagine the charge is in the center of the ball, and the electrostatic flux, let's change hands here so you can see what I'm doing. The electrostatic flux is coming straight out of this sphere at any point. Okay, so anywhere we move in the sphere, the electrostatic flux is perpendicular to the surface of the sphere. If we multiply the area of the sphere by the strength of the electric field, we then get the electrostatic flux. This is just analogous to the gravitational flux that we used to model gravitation in first semester. So the electrostatic flux is the product of the electric field and the product of the electric field in the area of the sphere. That's electrostatic flux about a point charge. It turns out that that flux is 4 pi kq. We can calculate that easily just using Coulomb's law. The electric field is kq over r squared. And the area of the sphere is 4 pi r squared. When we multiply them, we get 4 pi kq. The electric field at any point is the flux divided by the area. That is, the electric field on any sphere concentric with the point will be the total flux divided by the area of the sphere. And we'll do a lot more with flux in a few days here. Probably next time, as a matter of fact. Field lines represent the flux. So these field lines kind of represent the electromagnetic or the electrostatic flux emanating out from the charge. The denser the field lines are, the greater the electric field. We see that the field lines are much closer together on the first sphere than they are on the second. And if we drew another sphere further out, they would be even further apart, indicating the reduction of the electric field. So the electric field is going to be considered proportional to the density of the field lines.